Hello everyone, welcome to TLE Eliminators. Today we'll be discussing Leetcode Weekly Contest 453. Um, Before we get started, can just someone confirm on chat if I'm audible? Am I audible? Chat, okay. Before we start, I would like to inform you that if you're struggling to solve problems in contests like Leetcode, Code Forces, or CodeChef, and general competitive programming, or you have placements and you want to get better at coding or competitive programming or DSA, definitely do check out the TL Eliminators self-paced course, which is going on right now. The course is in 4 different levels, and it is oriented to all, stages of your journey, whether you're a complete beginner or you're an intermediate programmer. We, each level has different topics appropriate for the level. Like the starting level starts with time complexity, space complexity, searching, and it goes all the way to dynamic programming, trees, graphs, etc. The course features for more than 40 hours of recorded lectures and more than 100 curated practice problems. Each problem has dedicated hints and video solutions where the hints are incremental, like you get easier hints, then harder hints, and so on. And also, we have doubt support, dedicated doubt support team if you have any doubts, which is run by several high rated mentors, including myself. And so, yeah, good morning. Yes, good morning, Mr. Perfect. So yeah, let's get straight into the post-contest discussion. Lead Code Weekly 453. The contest this time was slightly easy on the easier side. What do you people think? And today we will do something slightly different. At the end of the contest, like at the end of the PCD, you can have like a general doubt discussion if you want, like any question you want, any question related to competitive programming. Hi, binary. So any question related to competitive programming or any doubt you have, or anywhere you're stuck at, or if you just want me to, give you some advice, you can put it in the chat at the end of the session and I will answer it. Okay. Today I'm not able to solve a single problem except the first. Yeah, well, that happens some days. Do not worry too much about it. Like from the first problem onwards, they were slightly, like the second problem was slightly tricky, and the third problem and fourth problem required DP ideas. So uh, if you haven't already taken the TLE course, I suggest taking it. And if you want to get familiar with those kinds of problems, like the second problem will be either level 2 or level 3-ish. Um, and then, the third and fourth problems use DP, so it would be level 4-ish, I would say. Yeah. Yeah, we'll answer general questions at the end, all right? Let's get started with the stream. Otherwise, um, like we won't do the PCD. I will answer all these questions at the end. All right. Okay. So transform array to all equal elements. That's our first question. You are given an integer array nums of size n containing only +1 and -1. Okay. So we are given an array which has only +1 and -1 and an integer k. We can perform the operation at most k times. Okay. Choose an index and multiply both nums of I and nums of I plus 1 by -1. Note that we can choose the same index I more than once in different operations. Return true if it is possible to make all elements of the array equal after at most k operation and false otherwise. Okay, so let us try to get an idea of what the question wants. So if we take any array, let's say 1, -1, 1, -1, comma 1. Okay, we need to make all the elements equal. And what is the operation we are given? We can multiply two adjacent positions by -1 at most k times. At most k times. Okay. So if we choose two adjacent positions, we can multiply with -1. And what does it mean to multiply with -1 for both these positions? It means we are simply flipping the sign. Okay. So we are flipping the sign. So what will this look like? So for example, for these two positions, it'll be like we change it to this, right? So now what is our goal? Our goal is make all elements equal. And what is a simplified version of our operation which we are allowed to do? Well, our operation is simply choose two adjacent elements, and flip the sign. Basically, we're multiplying with -1, right? So that's the what is happening. Flip the sign. And we can do this operation at most k times. At most k times. Okay. How do we go about this? Well, yeah. Okay. Yeah, chat. We'll do all these questions in the end. So let's discuss the problems in the contest first, because obviously up solving the problems in the contest which you could not solve, or at least even hearing the solution and implementing it does help a lot in future contests. So pay attention. Okay. So we can choose two adjacent elements and flip the sign. Um, so what is the intuition here? What is the intuition here? Well, the key piece of intuition is the final possible array. Like once we have made all elements equal, there are only two possible arrays which can come in the end. There are only two possible arrays which we can have in the end. One is where all the elements are equal and all are equal to 1, correct? So this is one of the possible ones. And the other possible one is where all the elements are equal and all are equal to -1. And why is that? Because we need all elements equal, and the only operation is flipping the sign. So either we could make it into all ones, or we can make it into all -1s. And there is no other option. So the approach I took, I'm sure there might be, for simple problems, there usually like multiple approaches, but the approach I took was very straightforward, very straightforward, very straightforward. Test both cases. So we will test both the cases. Okay. And how will we test both the cases? Well, let us first try to make it equal to all ones. If that fails, we'll try to make it to all -1s. If that also fails, then we can say no answer. Okay. So how will we test? So again, we can use one more idea. So this was our first idea or intuition. And our second idea is we can do a greedy algorithm. Greedy algorithm. And what do I mean by that? What I mean by that is, for example, we have this array and we want to make it equal to all ones. We want to make it equal to all ones. So what we have to do is we have to choose the first point where it is not equal to 1, and we can change that. We can change that. Like, see, this is the first point. It is not equal to 1. Here it's equal to 1. So we continue. Here it's not equal to 1. So we will flip the sign of this and the adjacent element. Okay, and why do I say that? I'll explain in a moment. So we flip the sign of this and this, and what do we get? We'll get we'll get this, right? Now, where is the first -1? Well, it's here, and we will flip the sign of this and this, and then what do we get? We get this, and now we can see that the array is all one, and the number of operations, or we can call that operation count maybe, that was 2. Since we flipped first here and then we flipped here, and then the whole array is equal to all ones, correct? So what is our idea? Find first point not equal to target. So first our target will be all ones, then our target will be all -1s. Flip that point, flip that element, flip that element and adjacent element. Repeat until all ones. Ensure that at most k elements were used, k operations were used, If this is not possible, if this is not possible, we can say false, right? And we should try both all ones and all negative ones. So if this is not possible, we'll try all negative one. If that is also not possible, and we'll try all negative one the same way. If that is also not possible, we can put false. In these two cases, of course, if it is possible, we'll return true. Okay. What is the proof for this? Like, how does the greedy algorithm work? Proof. Okay. So I'm going to explain a very brief proof for this. And the idea is really simple. Let's say we have this, right? This is our array. We have to convert this to all, let's say we have to convert this to all negative ones. Okay. So this is what we need to convert to. Why does it make sense to flip this first point of difference? Well, at the very first position, if they are not equal, there is only one operation affecting. There is only one operation affecting this position, right? One operation which can affect this position, because because there is no previous element, so there is no flip like this. We can only start flipping from the first element. So if the first element itself is wrong, then we must flip the first position, right? If the first position itself is not correct, we must flip the first position. So that's why we will flip the first position. All right. So now we get -1, and here we get +1, right? So here we get a +1, right? So this part became equal, and this part is now unequal. Now think about it. This prefix, which has already been fixed, like till here, it is matching, right? So here we cannot flip backwards. We cannot do a flip like this, because then it will undo what we did earlier, and there's no point to that, right? There's no point undoing what we did earlier. We can only think forwards. So again, if it is not matching, we will have to flip forwards, right? So this also becomes -1. This also becomes -1. I hope you understand that. So this is basically a proof. Then again, we can say that this prefix is matching, right? And till here also the prefix is matching. Now these two are not matching. So we can never make this array equal to all negative ones. So, we can return false for this case. We can obviously try all positive ones as well. So that is the basic idea. The first key intuition we had was that there can be only two possible final arrays. So that was our intuition. Then what we did, we used greedy idea to test both the cases. Each time it is not equal to our target, we'll flip that element and the adjacent element. And we gave a proof for why the greedy idea is correct. Now let us have a look at the code. First, let us discuss the time complexity. Since we are only going from I equals 0 to I equals n-1, and we are flipping anytime there's a mismatch, the final time complexity of this algorithm should simply be big O of n. There is no sorting involved. There is no fancy data structure involved, just an array or vector and just iteration and one loop. So the time complexity is big O of n. Okay. Let us have a look at the code. Okay. First, we obviously get the size. Then for the array, yeah, so what I'm doing is I'm making a copy of the array numbers called temporary, because I want to test two different cases, correct? I want to test all ones and all negative ones, and I don't want to lose my array. So that's why I'll make a copy of my array and I will do the operations on my copy. First, I will try all ones. So for each element from 0 to n-1, okay, for each element from 0 to n-2 technically, since we cannot do an operation on the last element. So if it is not equal to 1, I will multiply this and the next element by -1, right? And I will increase my counter. Finally, when this all is done, I will check if my counter of operations is less than or equal to k. And I will also check if my last element is equal to 1. Why am I checking my last element is equal to 1? Because there can be cases in which it's not even possible and the last element does not match. All the other elements will match because that's how we flipped them, but the last element may not match. So I will check if the last element is also matching, and in that case I will return true. Otherwise I will continue. Then I will try to match with -1. So it's the exact same code, except here I'm trying to check if it is -1. If it is not -1, I will flip this and the next element. And then again, I will check if less than k operations were used. And if the last element is -1, and then I return true. If both the cases don't work, I can return false. All right. So I hope this was understandable. It's the simplest problem in the set. Moving on to the next question. Anyone has any doubt on this, please ask in the chat. Doubt related to this problem, not general doubt. General doubts will address in the end. Any doubts, or should we move on to the next question? Okay, no doubts. Yeah, next question. So I found this also pretty simple question, but there is a trick. Like this is not a, if you understand the trick, you get it instantly. If you don't understand the trick, you might think it is very complicated. Some people who know advanced topics might start thinking about topological sort, things like that. But actually it is a very, very easy problem. And I'll show you how. Okay, you are given an array complexity of length n. There are n locked computers in a room with labels 0 to n minus 1. Okay, there are n computers. They are numbered 0 to n minus 1. Okay, each with a unique password. So each computer has its own unique password. Okay, the password of computer I has complexity, which is complexity of I. So complexity of I was the array which was given to us, and the password of the computer has that much complexity. Okay, the password for the computer 0 is already decrypted and it serves as the root. All other computers must be unlocked using the password for 0, or I mean the computer 0, or using another previously unlocked computer using the following information. Okay, you can decrypt the password for computer I using the password for computer J, where J is any integer less than I with a lower complexity. Okay, to decrypt the password for computer I, you must have already unlocked a computer J such that J less than I and complexity of J less than complexity of I. Okay, so basically, if we are given some computers and they're all in some order, like JI order, right? So we can write it something like this. Computer 0 is already unlocked, so we can mark that in green. Computer 0 is already unlocked. Each password has some complexity, right? And we can unlock any computer using some old computer like this. So we can use J to unlock computer I if the complexity of J is less than complexity of I. So if the complexity was 5 here and the complexity was 10 here, then we can use this to unlock this. But if it was the other way around, if it was 5 and this was 3, then we can't use this. Then we cannot use this. We can't use this to unlock this because the complexity is, the complexity of J should be lesser. Okay, so I hope that is understandable. The complexity should be lesser and the index should be lesser. Then only we can unlock the next computer. Okay. Now, what do we have to find itself? We have to find the number of permutations of 0, 1, 2 till n minus 1. Okay, that represent a valid order in which the computers can be unlocked. So we need to find some valid order of computers being unlocked with computer 0 as the only unlocked one initially. Since the answer might be large, return it modulo 10 to the power 9 plus 7. So if this is the first time you're doing these kinds of questions, know that modulo 10 power 9 plus 7 simply means that every step we need to take modulo of 10 power 9 plus 7. Okay. Note that the password for label 0 is decrypted. Yeah. Okay. Yeah. A permutation is an arrangement of all elements in array. So that I think everyone should know what a permutation is. Yeah. So let us take a look at an example. We have the complexity 1, 2, 3. So we have three computers. What would that look like? That will look something like this. Three computers. And what are the complexities? The complexities are, so C of I, we can call it C of I, and that is 1, 2, 3. So it's just increasing complexity. Okay. And what we can see here, we can see that this one is already unlocked, right? So the computer number 0 is already unlocked. Computer number 1 and computer number 2 are still locked. Okay. We need to find in which order we can unlock. Actually, the valid orders are 0, 1, 2, 0, 2, 1. So it says that the correct answer has these orders 0, 1, 2 and 0, 2, 1. Let us see why. Well, the simple idea is one way to unlock is simply put 0, 1, 2. So we can use the password of computer 0 to unlock computer 1 since the complexity is lesser. Then it says we can use the password of computer 2 to unlock the password of computer 1 to unlock computer 2. So one way of unlocking is like this. So this one is valid. And the other way is we can use 0 directly to unlock 2. So we can use like this. And then we can use 0 directly to unlock 1. So we get like this. So we get both these orders. Okay. Now let us look at the second example as well. The second example, it is not possible to unlock. And why is it not possible to unlock? Well, there are 5 computers and their complexity are 3, 3, 3, 4, 4. Okay. And the idea over here is we cannot use, okay, so in the start, only the first one is unlocked, right? So we have to somehow use the first one to unlock all the others. Now, the thing is, we cannot use the first one to unlock this or this, right? Since first one can only unlock ones with larger complexity. So therefore, since 3 equals 3, 3 equals 3, right? So we don't have, like, our condition is that the complexity must be lesser. It can't be greater than or equal to. So since we have two values which are equal to our first value, right? So we can never unlock these two. These two will always stay locked. So that's why it's not possible. So immediately we got one intuition. And what is that observation? First observation, we can say, if any element, so yeah, the number of ways for this case is 0, by the way. As you can see, it says the number of ways for this is 0, output is 0, 0. So yeah, if any element I greater than 0, okay, if any element which is not the first element in our complexity, right? So has complexity of I less than or equal to complexity of 0, right? Then there is no way to do this. Then return 0. And why is that? Well, there is no way to open, there is no way to, give the answer in this case, because then we can never even open the one with the smaller complexity. I hope that is clear, right? That is understandable. Yeah. Okay. So then what about the remaining elements, right? So in the remaining elements, what order of opening is possible? So this is what our remaining question becomes. So what order of opening is possible? Is possible, right? So this becomes our question. And now we will make an observation, okay? So we know that if any complexity is any point less than or equal to first one's complexity, let's say first one's complexity was 5, And at any point, if any computer's complexity is less than this, 3, so it's not possible. So we can return 0. So only valid cases are where the complexities are greater than the first one, right? So let's say these were the complexities. Okay. Um, how do we solve the problem? Well, think about it. If this one, the index of the first one is 0, right? The index of the first computer is 0. Also, we know that the first computer's complexity is less than all the others if for a valid case. So complexity of 0 is less than complexity of I for all the other cases, right? For all the other computers. So any computer can be opened using the first computer, right? Any computer can be opened. Any computer can be opened using the first one. Opened using the first one, right? So that means the trick here is that the remaining can be in any order, right? So we can, it's not exactly a trick, it's just very logical conclusion, but it can be in any order, right? But you can say that this is a bit tricky because, people will start thinking about, like the examples don't cover much. They just cover a case of n equals 3. So people might start thinking in some other, conditions for ordering and things like that. But we just need to observe that remaining elements can be in any order. So the question boils down to, so obviously first one will be unlocked first. First one will be unlocked first. And then the question boils down to how many permutations of remaining elements, right? Because we just showed that this can be opened in any order. And why can it be opened in any order? Because we can always unlock using the first element. So it does not matter which we unlock from, right? It just matters what are a valid ordering of unlocking. Be very clear about that. It only matters what is a valid order of unlocking. Okay. So we know that we can unlock it in any order. So what is any permutation where the first element is fixed and the remaining elements can be anything, right? So we need to find formula for that. And that is simple. Permutation of n minus 1 elements, n minus 1 elements, right? So that simply we can write as n minus 1 factorial, right? We can write that as n minus 1 factorial, and this will become the answer. So either the answer is 0 or the answer is n minus 1 factorial. I hope that makes sense. Uh, so while solving the problem itself, I had gone down some other route. Then I realized this simpler idea. So let me just remove one line from the code. The code for this problem is actually really simple, right? We simply have n equals the size of our complexity vector, and then what we can do is we need to just calculate n minus 1 factorial, right? So we just need basically 1 into 2 into 3 into n minus 1. So also we need to check if ever complexity of 0, if ever an element is less than complexity of 0. So in that case, we can simply return 0. Otherwise, we can multiply by I, take modulo. So then answer will contain factorial of n minus 1 and then return the answer. So this is a very simple solution to the problem. I hope the explanation was understandable. The key intuition is that basically any ordering of the n minus 1 elements is possible. And this is because we can always use the first computer to open any computer we wish. Is that understandable? Yeah. Will I give PDF of my handwritten solutions? Which PDF do you want the PDF of this, Ashutosh? Right? Yeah. Okay. Let's move on to the code. I already showed the code. It's a very short code. If ever the condition of complexity less than is violated, we return 0. Otherwise, we calculate n minus 1 factorial. Any doubts in this question? We can move on. Yeah. Okay. Ashutosh, can you just clarify what PDF do you want? If you want this PDF for this, I can put it on the YouTube comments uh, under the question. Okay. Let's go to problem C. Okay. Okay. Yeah, all right, I'll give that PDF then. Yeah, nice problem, nice problem, yes. Like I also like solving it. I also thought some weird thing in the start, and then I realized it was pretty simple. Okay, our first medium hardish problem, I guess, is also a medium problem only, but yeah, you can consider it. Like I found C and D to be about the same level itself, but yeah. Okay, count partitions with maximum difference at most k. You are given an integer nums and an integer k. Your task is to partition nums into one or more non-empty contiguous segments. What does that mean? It means basically subarrays. We need to partition into one or more non-empty subarrays, such that in each subarray, the difference between maximum and minimum elements is at most k. Okay? So return the total number of ways to partition nums under this condition. Since the answer may be large, again we need to do the modulo. Return it modulo 10 to the power 9 plus 7. Okay? So let us first understand the feel of our problem, since it is noticeably harder than the previous two. Let us think about it. Um, so let's say we are given nums, something like this, 9, 4. The question is straightforward to understand, I think. So, and k equals 4, right? So here the condition is the minimum and maximum of any subarray we choose, right? It can't go beyond 4. Like divided 1, this is 8, right? And this is greater than 4. So this will not be a valid subarray if we chose something like this, or if we chose something like this, right? We need to find number of ways to partition it such that the max minus min is greater than k. Sorry, is less than or equal to k. So how do we do that? Well, first let us just see this example. Let us see some cases. So here they always keep 9 separate. And why are they doing that? Because as soon as we make subarray 9, 4, we get 9 minus 4 equals 5, which is invalid because k is at most 4, right? Then we can have 4, 3. We can have this subarray, I guess, since the max difference, yeah, yeah. Since the max difference here we can see 4 minus 3, 4 minus 1 is 3, which is less than or equal to 4, right? And then we can have 7 separately. This is one way to split it. Otherwise, one way to split it is maybe like this. Yes. One way to split it could be, I guess this is also valid since 7 minus 3 is less than or equal to 4, right? So all these different ways are possible. And we need to count how many ways are possible. Okay. So what ideas do we get from this question? Well, at first it is a counting problem, right? It is a counting problem. So immediately, if you have studied DP, your mind should go towards DP, since it is usually a very good method to solve counting problems, right? Where we need to count number of ways. Since we need to count number of ways, number of ways. So the idea is that we will try to use DP, right? And how do you think about DP? Well, it's very simple actually. Like some people ask me many times, hey, how did you think about using DP? Hey, how did you think about using binary search? And the idea is once you look at a problem and if you have no idea, right? You have no idea how to solve it and you know some techniques, you know binary search is a technique, you know DP is a technique, you know greedy is a technique. They're not much techniques. They're like 10 techniques max. Think about trying to apply each one. Okay, if you're stuck for 5-10 minutes, just think, can I do DP? Okay, can I do binary search? Eventually, obviously one of these techniques will work, right? If you have studied enough, one of your techniques will work. So just think, okay, can it be applied? And especially since it's a counting problem, we know that DP is usually used to solve counting problems. So we can think about using DP. All right. Yeah. Okay. So I'll explain how we can DP this. So first of all, when looking at the problem, we can think like this. We can be like, let's say for each index, right? For each index, we calculate DP of I for each index, right? And that simply means the number of ways to partition max min partition less than equal to k for from 1 to from I equals 0, from let's say 0 to I basically, for the subarray 0 to I, right? So basically dp of I will solve the problem. dp of I will solve the problem for subarray, like solution of the problem for subarray 0 to I basically, 0 to I, 0 to I. Okay. So that's what we'll try our DP to be. Okay, so we'll say if the first I elements are done, then we'll try to solve for I plus 1. And then once I plus 1 answer, we know DP of I plus 1, then we'll solve for DP of I plus 2 and so on. Okay, that's going to be our main idea. And let us see how this can be done. Okay, so let's say we are in the middle of our array somewhere. Let's make the array bigger so we understand more clearly. 2, 3, 4, 5. Okay, and let's say we want to calculate dp of this element. So let's just call this dp of I. And we know that dp of all the previous elements is already computed, right? So we are computing from smaller I to bigger I. So dp of these elements is already computed and we are here. So if you are unfamiliar with dp topics, right? Obviously you can do the fourth course of TLE, right? Where DP is gone into in-depth. Some DP ideas have been covered in, I think, level 3 as well, but not that much, not as a proper topic. And of course, you can search for DP on the internet also. There's no problem in that. There is Eric To's video on DP in which he talks pretty well about, basic introduction to these ideas. So an idea of DP is a transition, right? So we need to find the good transition. In that transition, we can imagine that we are somewhere in the middle of our DP. We have already computed the previous elements. So this is one thing which Eric To also talked about. We're in the middle of our DP and we computed the previous elements. And we are going to figure out how to solve for DP of I. Okay. So we are at DP of I and all the previous elements are computed. So what we can do is one method is simply um, make this into a subarray. Okay. In that case, our answer is simply, well, there's only one way to make this a subarray, and then it will be simply dp of I minus 1, right? So our answer will simply be dp of I minus 1, okay, plus, and what we can have is, right? Then we can say, what about if we make both of these, okay? And let's say for our example, k equals 4 itself. And here we can, while we are making this subarray, we can check 7 minus 3, right? And here 7 minus 3 is less than or equal to 4. So this is a valid subarray. So that means we can choose this as our subarray, correct? We can choose this as our subarray. Then our number of ways to do the dp of I will get added with this choice. And then the number of ways to do this will simply be dp of I minus 2. And why is it I minus 2? Because simply we need to figure out how many ways to divide this. Then this will be same as taking this as one subarray and then dividing these into some subarrays. So our answer becomes dp of I minus 1 plus dp of I minus 2. But can we go to I minus 3? Can we go to I minus 3? Well, we will extend our subarray one more step. Okay. We will try from here. Okay. And here we can see that it is not possible. Why? Because max is 7, right? Min is 1, right? And 7 minus 1 is 6, which is greater than 4. So it's not possible. And everything beyond this is not possible. So for this value of dp, dp of I equals dp of I minus 1 plus dp of I plus minus 2. For this case, okay, for this case. Basically, dp of I equals dp of I minus 1 plus dp of I minus 2 plus so on plus dp of j minus 1. Okay. And what is j? J is the first position such that okay, such that um, from J to I, okay, first position such that, or you can say, uh, yeah, it should be simply dp of j, sorry. So it's going to be the first position such that from J to I, max minus min becomes greater than k. So it's the first position where it becomes greater than k. So we can see that the first position where it becomes greater than k is this position, right? So we're adding dp of I minus 1 and dp of I minus 2. So the first position where it becomes greater, till there we keep adding our dp. So dp of I minus 1, dp of I minus 2, all the way until this specific position, and we stop here, right? So we have to add the dp of this and this. Similarly, for let's say some position like here, okay, we can add this because the difference does not change. Here also, here we cannot add, right? Here, sorry, the 7 minus 2 becomes greater than 4. So basically, dp of this position will be the sum of this, and this. Okay, so that is going to be a dp idea, right? So let's call this idea 1 or something. Observation 1. dp of I equals sum of dp of I minus 1, dp of I minus 2, all the way till dp of j, where j is the first position such that max minus min becomes greater than k. Okay, that dp transition is understandable. By taking addition, are we not overcounting the ways? No, we are not overcounting the ways. No overcounting. Why? Because the addition law of combinatorics, right? If the events are disjoint, or if the ways of splitting are disjoint, then we can simply add the number of ways to find the answer, right? That's the addition law in combinatorics, addition identity. And we can see that all these conditions are disjoint. And why are they disjoint? Because here, if we split from 4 to 3, that means we're only taking one element. And this case is completely disjoint to all the cases where we have 3 and 4. And it is completely disjoint to all the cases we have 2, 3, and 4, right? Because these are disjoint, we can simply add those cases and we'll never overcount. Make sense? Yeah. Okay. But one problem we have with our logic so far is that if you look at the constraints say 5 times 10 to the power 4, right? And what we have done, our solution is n squared. Our solution is big O of n squared, but the constraints say, um, but the constraints say at most we can have, I guess, n log n or n root n, something like this, right? At most this much, because n over here equals uh 5 times 10 power 4. Wait, we went to a new page. N over here equals 5 times 10 power 4, right? So if you square this, this becomes bigger than 10 power 9. So we cannot do that, correct? So we have to find some way to reduce our dp to big O of n log n, something like that. Okay. And I will tell you the simplest method. I will tell you simplest method, okay, which I found simplest, at least, which I could think of. There are many ways to do this. There are many ways, right? There are many ways, including advanced topics like segment tree and stuff can be used here. But I will tell you very simple using only sets in C++. And basically what we want to know, we want to find J quickly, right? We want to find J quickly. And what is J? J is first position of max minus min becoming greater than K, right? Or in other words, it is last position, or one before the last position. One before means it's one step before the last position where max minus min was less than equal to K, right? In the subarray of from J to I like this, right? So in this subarray, the first position where this condition held, right? So how do we find that? What we can do is, so this also, I guess this takes some experience. Like if you have never seen this before, it might be hard to come up with it. But the idea is we'll maintain a window. Yeah, so this is a sliding window concept, which I guess is covered in level 2 or level 3 of TLE. So you can definitely check that out as well. Yeah, so it's a sliding window idea and maintain a sliding window, right? Ending at I such that the max of this window minus the min of this window is less than or equal to k. Okay, so we'll maintain the sliding window. Let's say at position, let's say our array was 9, 4, 1, that same example which we were using, right? 9, 4, 1, 3, 7. So at a position like 3, our sliding window will be these two elements, right? And a position like 7, our sliding window will be simply 3 or something like that, or 3 and 7, right? And then at position 3, it will be this sliding window. And how do we maintain this sliding window? Like as we go along, well, what we will do is we will store the elements of sliding window in a multiset, in a multiset. Why a multiset and not a set? Because elements can be repeated. And why are we using multiset? Because because insertion into the multiset, so insertion into, let's call it ms, is big O of log n. Removal of an element, removal is big O of log n. And also we can find max element and min element because set is always ordered. So set is always ordered. Set is, or multiset is also always ordered. So multiset is always ordered, right? So multiset is always ordered. So if you're using Java or Python, there'll be some equivalent of this, I suppose. So the way sets work is they use red black trees. So I guess in Java there is something called tree list or something. I'm not 100% sure what it is called since I don't use Java much. But yeah, there will be definitely some equivalent data structure. You can look it up. What is equivalent to set in Java or set in Python? You can use that. It should basically follow all these operations. Insertion should be log n, removal should be log n, finding max and min. So set can find max and min in big O of 1 since it's already ordered. But as long as you can find max and min in big O of log n also, that's also fine. So as long as you have a data structure which does all this, you're good to go. Okay. And what we can simply do is every time, let's say our current window is this much, right? Our current window is this much. We calculated the answer for this much, right? We calculated the answer for this much. Like we know the value of j. We know the value of j. J is simply one value before our window. Then if we want to increase our sliding window, what happens? Well, what happens is simply this new element gets added to set. So new element is added to set, right? Or added to our sliding window. Then if the condition of our set is violated, that means max minus min of our set has become greater than k, we can pop repeatedly from the start. Like we can remove this. You can cut these out until the condition is satisfied again. Fine. So basically, we move this one step front, and then until that condition is satisfied, we can pop from the multiset. That makes sense. Like if this becomes a new max or min, right? So it might become greater than k. So we keep removing until that condition becomes satisfied again. And how can we write this in C++ set? We can simply write if, or we can write while. It'll basically look something like this. Multiset.insert the current position. So let's say we inserted like this, right? Then while, so multiset.end will have the largest element. Uh, sorry, multiset.rbegin. If you know what rbegin is, it's a pointer to the last element minus multiset.begin. right? And this, while this is greater than k, we can remove the first element. So multiset dot erase, right? Multiset dot begin. Something like this we can do. And this ensures that our window moves ahead if the max, if the condition is violated, correct? So that's how we can maintain a sliding window, and that's how we can find the position of j. Now coming back to our DP, what did we say about our DP? Well, our DP of I is DP of I minus 1 plus DP of I minus 2 plus continuing DP of j, right? So we need to quickly calculate. So here, using the multiset, we found the value of j. So we can call this observation 2, and this is used to find the value of j, right? What was j? J is the last position where the condition holds. So now we need to find this value quickly. dp of I minus 1 plus dp of I minus 2 plus dp of j. And how do we find this quickly? Well, we can simply keep a prefix sums, right? So as if you have studied prefix sum, definitely if you see something like this, definitely you will know that we can use prefix sum, right? So how do we use prefix sum for this? We can simply maintain a prefix which has basically dp values prefixed, right? So prefix is prefix of I minus 1 plus dp of I. We can do this at each step of our DP. And then simply we can write dp of I will be prefix at I, right? Minus prefix at j minus 1. Prefix at I minus 1, yeah. So this is basically our answer, right? For each value of DP, we can get the prefix value still here, get the prefix value still j, subtract that. So we got this sum, and then we can continue. How are we maintaining the value of j? We are maintaining it using a sliding window approach. And the sliding window approach is handled by the multiset, which ensures that the condition is being met, right? Does that make sense? Yeah, tree map in Java, tree set. I'm not sure. Can't understand the transition. Okay, let me just revisit the transition. How does this transition work? Okay, so basically, we want to find number of ways to split from current I, right, into valid subarrays at this position I, right? So we will try all the subarrays one by one, like this, then this, then this, right? Until the condition becomes violated. Okay. And then each of those splits, each of these splits, 1, 2, 3, each is a valid split, right? So basically, this subarray is fixed, or this subarray is fixed, this subarray is fixed. There are three different ways to split at this position. And then the previous can be split in any way we want. So it will simply be the sum of dp of I minus 1 plus I minus 2 plus so on until j, such that the splitting is valid. Does that make sense? I hope that makes sense. So, like, I'm not sure how others ways to explain it, because that's the idea. At every position, we have either this or these two elements or these three elements, right? And each time when we do this, it becomes dp of I minus 1. So this plus dp of I minus 1 is the number of ways. Then when we take two elements, then it's dp of I minus 2, right? And we keep doing this until the condition max minus min less than equal to k holds. At any point that does not hold, then we cannot do this anymore for all those previous values. So basically our answer is sum of dp of I minus 1 plus dp of I minus 2 plus so on plus dp of j, where j is like the last position. We can do this idea. Make sense? And then how are we maintaining this? We are using a sliding window approach, and we are using prefix sums to quickly calculate the sum of dp in a range. Okay. Yeah, it is a slightly hard level question. Yeah. But then if you're used to DP, I guess it'll be fine. Like once you understand the n square logic, which is n square logic is very easy to be honest. then it becomes simply a problem of optimization. And there are many ways to optimize. Like I think this is the simplest way. There is also, some complicated ways to make this O of n. So the complexity of what I explained to you is O of n log n, since we're using multiset and set operations are log n. You can also use a segment tree approach. So segment tree can be used, but that is too advanced, so I'll not go into it. And there is also some approach with deck, which I think will work in O of n, but that is too advanced. So like that's not advanced, but that is complicated, and the only advantage is it becomes O of n. So yeah, um, you can also like use a segment tree to binary search the value of j. So we can find the first j such that max minus min is true, right? So we can use a segment tree to binary search the point. Like every point before this j, it will be max minus min will be true, while at this point max minus min will be false. So if we have a segment tree, we can use binary search, and that will be n log n squared. So the complexity is worse, and the method is also more complicated. So I try to explain the easiest method to do this. Yeah. Let us have a look at the code, which should clear it up. The code is actually not very long. The code is pretty simple. Okay. First, I'm defining my mod on top. Okay. Now, okay. So one thing in my code, I used one index DP. Why did I use one index DP? So DP of one means from uh, till I minus one, number of ways till I minus one. And why did I do that? That is simply because prefix sum is much easy if you start at prefix of zero, right? Because I can just set prefix of zero and then I don't need to check too many cases. If anyone has, like, if you have studied prefix sum, you know that one indexing is often easy with prefix sum. So yeah, I have DP of size n minus as n plus one, prefix of size n plus one. Our base case DP of zero, prefix of zero equals one. Why did I write that? This is the base case. Okay, base case. And how do we get our base case? Well, right. So our base case simply means this, right? So there is no actual zero, like there can't be n equals zero in the question. But here we're assuming that if there's an empty subarray, what is the answer, right? And if there's an empty subarray in the start of our array, then the number of ways this can be divided into subarrays satisfying the condition is obviously one, correct? Since an empty subarray cannot even be divided, like there's only one way to divide it, that is to keep it unchanged. That's why DP of zero equals prefix of zero equals one. And this is going to be our base case. Obviously, if you can write a base case with DP of one, right? That also you can write, but that becomes a bit complicated. Like it's just to simplify, that's why I've written it like this. So yeah, now I'm going to create my multiset. This will hold our sliding window, right? This is going to be our sliding window. L equals zero. Okay, what is L? L is our J basically. So what I was explaining as J, in the code it is as L. So this is our J. Okay. Then what do I do? Each time from one equals to from dp of I, dp of one to dp of n, I insert nums of I minus one. So I'm inserting the next element. I'm doing the multiset operation. So while the multiset's largest element minus the smallest element is greater than k, I pop the first element of my multiset and I do L plus plus or J plus plus. So basically I'm erasing the first element and I'm increasing L until the condition becomes satisfied again. Okay. So once this has happened, I simply need to take basically dp of I minus one plus dp of I minus two all the way till dp of L minus one. So my answer is going to be like this, right? So my answer is going to be like this. Obviously, we need to take mod over here, right? So then I can simplify this since I'm already taking prefix sum. I can simplify this to prefix of I minus one minus prefix of L minus one. If L minus one is greater than or equal to zero, of course. So that is the code I've written here. Prefix of I minus one minus prefix of L minus one. If L minus one is greater than or equal to zero, otherwise it will be simply zero over here. And why did I write this minus this plus mod percent mod? Because whenever you want to write a minus b, you want something mod, right? You need to write it like this in C++ at least. Otherwise, you will get garbage values sometimes. So this is how we write a minus b percent mod. So it should be a minus b plus mod percent mod. Otherwise, it becomes a negative number, and taking mod of negative number gives invalid like answers in C++. And then simply we compute our prefix sum. So prefix of I is prefix of I minus 1 plus dp of I percent mod. Here also we have to take mod for sure. And then we return dp of n, which is the number of ways to split into subarrays. Does that make sense? Can you please rate the questions of Leetcode contests according to ratings? So I don't know how exactly to Leetcode ratings work, but according to me, I guess problem A on code forces, I can say it would be roughly 800 to 900. Problem B also would be like in code forces rating maybe 900 to 1000 maybe max 1000 I guess about 900. Problem C should be in my opinion 1400-ish on CF, right? Roughly because it uses DP, it uses prefix sum, it uses multiset. So yeah, it should be around 1400 on code forces. And D should be again, I guess, maybe 1500. In my opinion, I found D easy. Maybe you could say it's 1500, 1600 D. So for this contest, this would be the rough ratings. My opinion only. It could be wrong. Like, so what is easy for me might be hard for others. What is hard for others might be easy for me. This is my opinion of this contest. Okay, let's move on to the next question. Right? Minimum steps to convert string with operations. All right, let's move on to the next question. Yeah. Okay. Problem D. Okay. You're given two strings, word1 and word2. To be honest, I found D easy, on the easy side for usual Leetcode D. So you're given two strings, word1 and word2 of equal length, you need to transform word1 into word2. Okay. For this, divide word1 into one or more contiguous substrings. So very similar-ish problem, I think. For each substring, you can perform the following operations. Replace. So that means replace the character at any one index of substring with another lowercase English character. Okay. Swap. Swap means we can swap any two characters in the substring. Reverse substring, which means reverse the substring. So we can divide it into different substrings and then we can perform these operations. So let's say our substrings were, let's say our words were hello and something like heli or something, right? So we can divide this into substrings like this. So something like this we can divide maybe. Then this one we can reverse, and in this one we can change O for B, and we can do it in two operations, right? So we need to transform word1 into word2. We can divide it into substrings. We can perform these three operations. Each of these counts as one operation, and each character of each substring can be used in each type of operation at most once. At most once. So no single index may be involved in more than one replace, one swap, or one reverse. What does that mean? That means that some given index, okay, so let's say we had hello, and then let's say this substring we chose, okay. Now each index can be used in at most one reversal, at most one replacement, and at most one swap. So that means that we can't do two swaps like this. We can't change it like EL got swapped, we became LELO. Then we can't swap these two. Like we can't swap like this and then get and then get like this. Okay, we can't do two operations of the same type at one position. So at this position and this position, we did like the same operation twice, right? So we cannot do two operations of the same type at one position. That's what it means. So each of these counts as one operation, and each character of each substring can be used in each type of operation at most once. Return the minimum number of operations required to transform word 1 into word 2. A substring is a contiguous non-empty subsequence of the characters, is non-empty sequence of characters within a string. Make sense? Yeah. Thank you for that, Aditya. Okay. Okay. So here again, we're going to think of a DP idea, right? And one very important thing to pay attention to here is the length is at most 100. Okay. Our length is at most 100. So what does this mean? That means up to O to the N4 solutions are allowed. Okay. Because the length is at most 100, up to big O of N to the power 4 solutions will be allowed. And so we can think of more brute force type of ideas as well to figure out the solution. And we have to count minimum number of operations, right? So here again, we're going to use a kind of DP idea. And the DP idea is going to be something like this. So let me write string, our elements of string like this. So these are just placeholders for the characters in our string. Okay. And this is our second string. So I'm going to call it T. T means target, right? So this is what we want to achieve. Okay. T8. Okay. Now let dp of n, okay, that will be the answer. So the answer is basically minimum number of operations to make this whole thing equal to this whole thing, right? And dp of I, what will be dp of I? dp of I will be for each position, how to make it equal. So at dp of 5, let's say, it will be the value to make this equal to this. Make sense? So once we know, like for each, how to, what is the minimum number of operations to make them equal using the given, idea, then we can, using the values of previous, like once we have computed this much, using the value up to I minus 1, we will somehow figure out the value of dp of I. Okay. So that's going to be a general approach to this problem. So how do we do our transition? Okay. So first of all, we'll use a very similar idea to last time. Since we have to split it into substrings, last time we had to split it into subarrays, we can consider at every I, we can consider this as one substring, right? Then this as another substring, and then this as another substring, so on. So all these possible prefixes as substrings. We will find the answer for this substring, and here we will use dp of 2, correct? So answer for dp of 5 will be equal to max of, right? Sorry, min of, since we want to find min operations. So it will be min of either taking this and then this. So number of operations for this substring, like we can say 5, 5, right? So this substring. So, and then plus dp of 4, right? So this substring we are treating as we can use these three operations. And for the previous, we can use dp of 4, which we have already computed. Then otherwise we can take these two, right? So that's another value in our min. So it'll be dp of 3 plus answer for 4 and 5, right? Plus dp of 2 plus answer for 3 to 5, right? So we find the answer for this much. And for this, we take its dp value, right? And so on. And this is how we're going to compute the transition for our dp set. So let me write the transition clearly. Our transition is going to be dp of I, okay, is min of dp of j plus, or maybe we can say dp of j minus 1 plus the answer. Answer means using these two operations on that given substring, these three operations on that given substring, what is the minimum? So we'll figure out how to implement answer later. For now, we're writing the dp. So answer for the subarray. So subarray j till I, right? So this minimum for all j less than or equal to I. Okay. So this is going to be our transition for our dp. Does that make sense? It's very similar to the last problem, except there is no sliding window to make sure that any condition or anything like that is holding. Okay. So this is going to be our transition. Now this will be n squared again, right? This will be n squared again. So what is the cost for this? The cost for this is simply big O of n squared, big O of n squared times, of course, the complexity for answer, of course. So whatever complexity that takes, right? So rough complexity is this. And since we have up to n to the power 4, we can definitely do this. We just need this big O of answer to be not too bad, kind of, right? Number of operations, finding the answer for some subarray to not be too bad. Okay. So now what we have to do is basically implement that function. Implement a function of at most big O of n squared. What happened? Just a second, sorry about that. Of at most big O of n squared such that it takes a subarray, which is our, or substring actually, whatever you want to call it. Doesn't matter. Array is simply a string is simply an array of characters. So it takes a substring for our word from basically s of j to s of I, and it tries to make it equal to target of j till target of I, right? And it uses these three operations, using these three operations, and it does it at most once, right? At most once per operation per position. That's what is given. Once per operation per position, we can use the operation, these three operations, right? So this is what we need to implement, and using this DP, our whole problem will be solved if we manage to implement this correctly. Fine. Does that make sense? Can anyone tell in the chat if that makes sense? Since we are basically kind of doing a very basic DP, we're checking every subarray, and we are doing like DP of like we're checking this, then we're checking this, then we're checking this, and so on, all the way till 1, right? And then we're calculating the manual answer for this, and for this we're using the DP answer. And so that's a very straightforward DP in my opinion. Now we simply need to implement this function, which can, given a subarray from j to I, it needs to make it to target, it needs to make it to the target values using these three operations. Each operation can be used at most once per operation per position, right? So one position can have at most one of each of those three operations. Well, first thing we can write, for each subarray, either we use reversal or not, or substring. Either we used reversal or not. Okay. We can call this observation 1, and this can be our observation 2, I guess. So for each string, either we use reversal operation or not, each substring, right? So in our original example, let's say hello, where we had ELL, right? So let's say we were solving for hello, right? then uh, then when we are at this position, we might have called this function, and here we're using simply dp of 0, dp of 1 plus answer from 2 to 4, right? And when we're calling from 2 to 4, either we can try doing this with swaps, and we can use swaps and what is the first operation? Replacements, right? So replacement and swaps, or we can reverse, then try replacement and swaps. And why are we saying that this is the only two cases we can have? Well, we know that we must, if we are going to reverse substring, we must reverse the whole substring, right? So reversal reverses the whole substring. Reversal does it to the whole substring under consideration, right? And again, remember the rule, at most one operation, each operation at most one set of position, right? Each operation at most one set of position. So we can only reverse once, not twice. We can't reverse, do some swaps and reverse again, right? So that's why we can only reverse once. So basically what we're going to do is we can test basically using only swaps. So if we define, let's say, answer of I, answer of, let's say, ji. So this will be the substring from j to I, how to make it equal to the target. Then using only swaps, and replacement operations, right? Using only swap replace operations. Then we can check both S of j of I and reverse of S of j of I. And we can take minimum of two cases, right? So in this, we already did one operation of reversal, and in this, we did no operations. So we first find using only swaps and replace for this. Then we reverse the string, find swaps and replace, how many minimum operations we can do, and then best of two cases we can take. So basically this point itself, best of two, either reverse substring or not. Okay, so this is our intuition. Either we reverse initially or we don't. There's no point reversing later on, because if we reverse initially and do some swaps, it's the same as doing some swaps and reversing later. So the answer doesn't change. So either we reverse or not, and then we try to do the swap and replace operations. Now, how to implement the swap and replace operations? Okay. So let's say two strings we have, and we need to make them equal. Now at these two positions, they're already equal, right? So let's write a target actually. So let's say a target is something like this. Okay. Uh, okay. So this is our substring. This is our target substring, right? So first we will consider with reversal and without reversal. So this is without reversal. And here we can see that A and B are equal already, right? A and B are equal, so do nothing. A and B are equal, do nothing. B and C are not equal, right? So now we need to find if there is some swap or there is some replacement. So obviously we can do replacement and we can write B here. Right? Sorry, we can do replacement and we can write C here, right? But also we can do swap. So we can swap these two. Then this will become C, this will become B, and both of them will match, correct? And both will match if we swap, right? And so this costs us only one operation instead of two. So one operation instead of two. Like if we did replacements, it would have taken two operations. So here it's taking one operation instead of two. So it's better to swap when we can. It's better to swap when we can, right? So that is our key idea. And basically, when can we swap? We can swap when S of I, so let I and J be two positions, right? And we can swap anywhere in the array. Make sure it's not just adjacent, it's any two characters. So we can swap when any s of I is not equal to target, right? So it should not be equal to target of I, right? Otherwise there's no point, it's already fixed. So if this is true, and also s of I is target of j, okay? S of I equals target of j, and S of j equals target of I. In these cases only, swapping is beneficial, right? Otherwise, if we swap, if this does not hold, then replacement also will cost you the same itself. So we will swap in basically positions like this, in positions where this is your I, this is your j, and this is equal, correct? Then we can swap, and in one operation, here we'll have CC, here we'll have BB. So we can have both strings match in one operation. So swapping is only beneficial in when this condition holds. Does that make sense? Yeah, that makes sense. Thank you. Okay, so yeah. So what is our idea going to be basically for how do we implement answer of substring j of I, which is what we wanted to finish our DP idea? Well, simply we will try both reverse and non-reversed. Try non-reversed and reversed version and reversed version. And what will we try on that? We will find minimum steps, find min steps using swap and replace, right? Operations. And how will we find this? Well, here is the key idea intuition behind this. I think this is the most important intuition of the problem, although it might be very simple for most people, I guess. And the key intuition is greedily swap when you can. Greedily swap when you can. If the string is substring which we are considering is not equal to target and we can swap, then we will do the swap. Otherwise, use replacement operation. Okay. And what does this look like in code? Basically, it's like for, let's say the substring starts at 0 and goes till n. Okay, just for example. So for 0 to n minus 1, if s of I is not equal to target, or if it's equal to target, then we can just continue from this position, right? If it's equal to target, then we can continue, right? If it's not equal, then only we need to do either swap or replacement. Then we can simply check for j from I plus 1 till n minus 1, right? If the swap condition is satisfied. So if the swap condition is satisfied means if s of I equals target of j and if s of j equals target of I, right? This is the condition we discussed, because then we can swap. Then swapping will fix both of them. If we have B and C, here we have C and B, then swapping these two will fix both of them, right? In this case, we swap these two. Swap s of I, s of j, and count. So we'll count the minimum number of operations, right? So we'll increase our counter. And if we went through this, so once this swapping is done, we can break here, right? We can break from this loop, j loop. And then if it is still not equal, that means swapping did not make it equal, right? So if still s of I is not equal to s of j, then we'll have to replace. So basically, we can replace s of I equals target of I. And again, we can increase the counter because there's no way to swap and fix this position. So we must use the replacement operation to fix this position. So basically the key idea is again greedy. So here we're doing a greedy. And what is our greedy? Our greedy is that since swap operation is better than the replacement operation, it saves one step. Whenever we can do the swap operation, we'll do it. And it will save one cost, right? And this is the condition for doing the swap operation. Basically, if these two are equal, right? Otherwise, there's no use of doing the swap operation. We can simply do replacement operation. Because only in this case, swap operation is going to save us one step. So if we implement this function in our DP transition, which we discussed all the way back, then we have solved the problem. And this solution is, since this is two loops, from I to j, I to j. And again in our DP, we had two loops as we discussed. And this is n squared now. So our final time complexity is big O of n squared. And I think if you know DP, this solution should seem very easy to you, n squared times n squared. So it's big O of n to the power 4. And this is our final time complexity for this problem. Let us have a quick look at the code for how this works. First, let's look at the main function or the DP function. Here again, I decided to DP, which is one indexed. So I hope you don't mind that. N is simply the size of the word. We define a DP. We set it to int max since we're trying to find minimum, right? DP of 0 is simply 0 because the minimum number of ways to match a string of size 0 is simply 0. Then from I equals 1 to n, j equals I minus 1 to 0, right? So we're checking from j equals I minus 1 to 0. Why is that? That's what the DP transition says for all j less than 0. So we're checking this, then we're checking this, and this, then this, right? I am taking the substring, right? So word1 dot substring, word2 dot substring, I'm storing those. You don't need to store those, you can just directly push them into the function, no problem. But yeah, the way substring works in C++ is you need the starting position and you need the length. So basically that's what I did. So from j to I minus j. In Python, we can simply use like start at j comma this thing. Like substrings are very easy to take in Python. This is how you take in C++. Then from dp of I, so dp of I equals min of dp of I plus dp of j. This is how we discussed. So till j, we are simply taking the dp. And then from that point onwards, we're taking the substring's answer. So we're going to match this to this. Otherwise, we reverse. And then dp of I equals min of dp of I, dp of j plus 1 plus the answer. And why plus 1? Because reversal itself is an operation. So we're taking min of both the cases without reversal and with reversal. Now, how is the answer function working? Well, count is going to be the minimum operations and simply the size of this substring. And it's exactly what we discussed in the pseudocode for answer. We're counting the minimum ways to do it with swapping or with replacement. So for I from 1 to n, for j from I plus 1 to n, if we can swap these two, we try to swap, right? If we can swap, we try to swap and we break. And if the swapping did not work, we have to do a replacement and we increase the counter, right? If the values are equal already, we can just continue to the next point and we can return the count of the operations. So that's it. In the end, once the DP is done, it'll give you the final answer, right? So you need to be familiar with DP. You need to be familiar with gritty ideas to solve this. So TLE level 4, I guess. Yeah. You have learned DP from Strivers, where it explains recursive, memoization, and bottom-up. Well, once you come to harder problems, you should get comfortable with doing directly bottom-up. That's my opinion, Nihal. Like, if you actually want to solve these problems in contests, you want to become very comfortable with bottom-up DP. And if you want to have recursive understanding, I can give you right now. But look, recursive understanding, like at a certain stage, till a certain stage, it is helpful, right? Till a certain stage is helpful. But at some point, um, switch to bottom up first. Switch to bottom up because, like, if you observe, like I think or someone said, 90% of top CTOs, like who are very highlighted, they all think bottom up itself, right? That's because bottom up is easier to think at some point. And I suggest, like, Edictor's videos, they go through bottom up ways of thinking. But for you, I will do a recursive way of explaining it. Basically, um, the recursive function for this would be something like this. So dp of, let's say something like this. So what it will be simply for j starting at I, going all the way to 0, right? We will recurse into dp of j plus the answer from j to I. It's actually very similar, even if you write it recursively. So if the answer is int max here, answer will become min of this and our answer. Maybe I should write this more neatly. So I'll just write this very neatly. Um, I'm assuming that you know how to memorize, so I won't write the memorization here. You'll have to memorize it yourself, otherwise this will give you TLE. All right. So for j less than or equal to I, right? Um, so let's call this function f, right? Let's call this function answer over here. Let's call it f for now. So it'll be simply minimum of answer f of substring, the substring which is from j to I, right? Plus dp of j. So if it's one index, it will be dp of j, something like that, right? Then we reverse the substring. So let the reverse substring be rs or something. So rev sub, I guess, reverse substring plus 1 plus dp of j. So you can imagine this is a function call, right? And then if we memorize this, this will do the exact same thing. This is the top-down dp, I guess. Return answer. And our final answer will be simply return dp of n. Okay. And the base case is if I equals 0, return 0. And what is this doing? This is basically saying at the last position. So what is this doing? Again, we can go back to the same array and show how it works. So at a given position, we can, let's say if our I was somewhere here, right? Our I was somewhere here. So first we try this subarray and then we take dp of this. So dp of 7, right? Then we try this subarray and we take dp of 6, right? So we solve this subarray using either reversal or unreversed and we add dp of 6. Otherwise, we try this subarray, we add dp of 5, right? So, and if we memorize this, then at dp of 7, we don't have to recompute dp of 6 and so on. That makes sense? Can you tell what resources help you build your logic? Well, if you study DP for a month, I'm pretty sure you would be able to solve both of these questions, C and D. So I think TLE level 4 is more than enough doing the TLE level 4 and problems. But if you want, obviously, competitive programming handbook, if you have not heard about it, that's a great resource. And solving a lot of problems, obviously, because DP is something you learn only by solving. So yeah. Thanks for the PCD. Please share notes. Definitely, definitely. I will soon, maybe in 1 or 2 hours it might take, but I'll post it on the YouTube comments. Okay. Let's just wrap up by finalizing the time complexity. Again, the time complexity of either approach, if you memorize, will simply be big O of n squared. Okay. So n to the power 4, n squared into n squared. dp is n squared and the function is n squared, so n power 4. Okay. Any other questions? Any general questions? Since we have discussed everything, you may ask me anything you want. I can address any old questions which you had. Shankar, you just need to practice. Like, I'm a complete beginner for Leetcode. I'm learning DSA, but I'm unable to solve problems and the logic is not building. So if you're here, Shankar, there is no substitute for practice. What I can say is do questions, slightly above your level. Like that's a commonly heard tip, but it is the most important thing. So if in a contest you could solve one problem, then you must upsolve second problem, right? And then if you could solve two problems, you must upsolve the third problem. If you could solve three problems, you must upsolve the fourth problem. If you could solve all four questions, then you're obviously doing a contest which is too easy for you and you should do harder contests, right? Um, that's how you improve. And if you can see that usually I solve two problems, usually I solve one problem, then you can see, right, in previous contests, the second problem or the third problem, you can solve all of those. You can see what rating those roughly fall into, and you can solve that level of questions. So basically, um, find which rating you're stuck at. Uh, just a sec. Find which rating you're stuck at, which rating problems you're having difficulty with, you're stuck at, right? And solve more of those. And it should not be too hard, right? It should be just where you're stuck. Solve more of those. So if you could not solve, let's say B in this contest, then I think you should solve more of 1,000 rated problems. You should get used to familiarizing yourself with those. If you could not solve C, then you should solve maybe 1,300, 1,400. I'm telling you according to CF rating. Leetcode does not give, I think, that standard rating, so that's my advice. Obviously, you can do the TLE course and do practice problems from those. Okay. After Striver DSO sheet. Hmm. Actually, I should answer new questions first, so let's see. Hi, is it possible to enroll in the TLE course and pay it with USD? I'm not 100% sure about that. I guess um, I guess I will have to ask someone who's in in charge of the finances. But if you put that in the YouTube comment section, I can reply to it. Fan and definitely. And I'm sure it will be possible to convert it into some form and then pay. I'm pretty sure. Why is there an unnecessary ban for a month? Well, I cannot tell you why you got banned, Ankit. Either your code was maybe similar to someone else's or something like that. Um, Definitely do not use IDEs. Don't use online IDEs because online IDEs make your code public, so someone might see it and then you might also get flagged, something like that. And definitely, if you use ChatGPT or anything, then you cannot, they will ban you. So otherwise, if it was an honest mistake, I guess there'll be some method to appeal it. So yeah. Any other questions? Can you tell us what resources helped me? So personally, I was like I practiced for Olympiads. So if you're not sure about what those are, so in 11th, 12th, I practiced for Olympiads. I used some Olympiad resources, and then in college, once I came to college, I started CP more seriously, and then I mostly solved code forces. Like in the start, I was getting stuck in like div to C. So what my idea was, I solved 20, 30 questions of div to C, and then after that, div to C became fine. Then after div to D, I used to get stuck at. So I solved again 30, 40 questions of div to D. And of course, I learned all the basic and important concepts like dynamic programming. I solved 10, 20 questions from dynamic programming. And everyone requires a different number of questions to become good. So solve until it becomes easy for you. So I learned dynamic programming, greedy, binary search, of course. I use stuff like Code Forces EDU, USACO, stuff like that. I am drilling but can't do good in contest. So see, don't worry about that. For everyone that happens, right? So when you're practicing, it's something like latent heat. If you have studied latent heat in physics, so that's like how I like to think about it. So when you're doing latent heat, if you heat water, right, for a while it does not show any visible change in temperature, but there is some change happening internally which you cannot see, right? So for some time, even though you're practicing, right, you won't see much change in your rating for a while. That's because your body is still getting used to stabilizing and working at that performance. Even though you're internally getting better, your contest will not reflect. And then suddenly you will have some jump in rating. And then again, you will practice a little and your rating will jump. So that's what I've seen most people's rating goes up by. So don't worry too much. Keep practicing. Be consistent about it. Ankit, what is your if I have to start DP, I am also preparing for upcoming off-campus internship. Well, yeah, see, of course you must balance your time. So like You can maybe make sometimes. See, Ankit, almost any resource is good, right? Um, as long as the resource is written, most of the resources available on the internet are very good. But personally, as a member of TLE, I am definitely sure about TLE's course because that's what I've gone through. I've seen the stuff there. I'm even helping making videos for it. So yeah, I will definitely recommend TLE's course. But then many of the courses like Competitive Programmer's Handbook and stuff are very good. So you should definitely, when you decide on a resource, don't second guess it. Just stick to it. Stick to it for 6 months, 8 months until it becomes easy for you, and then only move on to the next resource. A lot of people keep switching resources and then never follow anything in the end. So definitely don't do that. Yeah. How much should we practice? I generally solve 3 to 4 questions a day. Is it enough? So again, practice depends on you. But if you're solving 3 to 4 questions a day, I definitely think, see, you must solve one question which is hard for you, one question which takes you 1 or 2 hours. So if you are doing a question like that every day, then definitely you will see an improvement very fast. But if you're doing 3 to 4 questions and they're very easy questions, you will not see much improvement. If they're all questions which can do in 5-10 minutes, you will not see any improvement. Even if you do one question a day, right, which is hard enough, which is like above your level that it took you 1-2 hour, but you solved it, that is, in my opinion, that is more than enough practice if you do one question well. But yeah, 3 to 4 questions is definitely a good and maintainable amount to do every day. So yeah, again, it depends from person to person, right? Everyone's starting point is different. Everyone's learning speed is different. 3 to 4 is a good spot. That is enough. You don't need to do more than 3 to 4. Try to increase the quality of your questions rather than the number. Okay. That is my advice. I personally, if you see, have not done that many questions compared to most people. I have tried to extract more value per question rather than do more questions. And that is my philosophy. Of course, everyone has their own philosophy. So yeah, in the end, it all boils down to practice. How to choose rating. Okay. Like I explained, that's very simple. Take your last 5 contests, right? Take your last 5 contests and find out which question you solved till. Let's say you solved ABC, you got stuck on D, right? And in another contest, you solved AB, you got stuck on C, right? And then you find the rating of these, right? Like if let's say D had a rating 1200, C had a rating 1300, and then in this contest, D had a rating of 1500. Just take like a rough average or this interval and solve in that range because that is the place you're getting stuck. Yes, your rating becomes stagnant. See, like I said, it's like the latent heat thing. For a while, your rating is stagnant, even if you're becoming better. So do not use rating to a judge of your progress, current progress, because rating happens after progress. Progress does not happen after your rating increases. Your rating increases after you have done progress. So that's why your rating will always lag behind your current level. Don't worry too much about that. Just practice. It becomes better. It'll suddenly become better someday, and you don't even know like how it become that much better, right? And the amount of time it takes to become better is different for everyone. Well, okay, I hope the advice helped. Um, this is my views on it. Of course, everyone has their own views. Any other questions? Otherwise, we can end the stream now. Thank you very much, everyone, for attending, and do check out TLE's course. I hope the explanation was understandable, and see you next time.